Hi everyone, this is Class 9 for PH 125, and today we're going to be continuing to discuss 2D kinematics. Specifically, we're going to apply our 2D kinematics equations to a special example of projectile motion. This is the two-dimensional equivalent of free fall. Okay, so to get started for today, let's just remind ourselves about our kinematics terms, which we covered in the last lecture. So just a reminder, we're going to be talking about position, displacement, velocity, and acceleration, where position is location relative to a defined coordinate system, displacement is change in position, velocity is the rate of change of position, and acceleration is the rate of change of velocity. And these definitions are all the same as what we learned when we were talking about kinematics in one dimension. However, now we're going to allow our motion to expand into two dimensions. Okay, and so to do that, we're really going to be using the same basic definitions of these different properties, except now each of these properties can be in two dimensions. So in other words, they can each have x and y components. Okay, and so then our goal in the next chapter is going to be understanding how these different kinematics properties are related to each other for an object that has motion in two dimensions. All right, so that was really a wrap on Chapter 3. We really finished it up in the last lecture. Today we're going to be starting on Chapter 4, which is all about two-dimensional motion and the kinematics equations of motion in two dimensions. Okay, so as I mentioned, our goal in this chapter is going to be understanding motion in two dimensions. So we want to understand things like displacement, velocity, and acceleration. Now we want to think about things that can move in two dimensions, not just in a straight line, like we were studying in Chapter 2. And so to start on this study, I just want us to look at this quick demonstration where there are two balls dropped from this apparatus. So here you can see we have this apparatus and there's a ball being placed on the left-hand side of the apparatus. That ball is just going to be dropped vertically, so it's only going to be moving in one dimension, and so we can think about it in terms of the things that we learned in Chapter 2. Then there's going to be a second ball that's placed on the right-hand side, and that ball is going to be given two-dimensional motion by being shot out to the side, so it's going to have both horizontal and vertical motion. And as you watch this demonstration, I want you to think specifically about when these two different balls land. Okay, and so you can see here that the two balls land at the exact same time. And this is a very interesting thing. You might not expect that the two balls would land at the same time. And so our big question is going to be, why would those two balls land at the same time? So how could we explain the fact that the ball that's launched horizontally lands at the same time as the ball that's just dropped vertically? Well, really, when we think about this, it has to be true that motion in the horizontal and vertical directions must be independent. That's the only way that we could have the two balls landing at the same time. So in other words, they're falling the same distance in the y direction in the same amount of time, even though one of the balls also has horizontal motion, while the other only has this vertical motion. So the fact that this second ball has horizontal motion must not affect the motion of the ball in the y direction. In other words, the horizontal and vertical motion are independent. Okay, and so then this is really important and it's really nice for us, because it tells us that we can actually use the same modeling that we used in one dimension when we think about motion in two dimensions. Now all we have to do is think about separating the motion in two dimensions up into vertical and horizontal components. All right, and so what that means for us specifically, when we think about, for example, motion with constant acceleration like we studied in one dimension, now it's pretty straightforward to think about generalizing that into two dimensions. All we have to do is break our position, velocity, and acceleration vectors up into x and y components, and then study that motion in the x direction and the y direction separately. Okay, and so how are we actually going to do that? Well, we're just going to use our same equations of motion in the case of constant acceleration that we learned in Chapter 2. So I have 3 of the 5 listed in this table here. These are the main 3 that we'll be using. So I have those original equations, and now we're just going to translate into two dimensions by breaking all of our important kinematics properties up into their x and y components. So for example, what we want to do is we want to think about position and its components in the x and y directions. We want to think about velocity and its components in the x and y directions. And then finally, we want to take acceleration and break it up into x and y components as well. And then we take our original equations of motion, which just were originally derived from motion along a straight line, and we're just going to separate them out into two sets of equations, one for all x components and the other for all y components. So you can see that the basic building blocks of these equations are the same. Now we've just said, okay, we only have x components of our position, velocity, and acceleration, or we only have y components. We never want to mix those two. Okay, so let's take a closer look at these equations before we start using them a little bit. And we just want to remind ourselves about what each of the variables in these equations really stands for. So this is something that's really important. You're going to want to think about this a lot whenever you get a problem statement. You'll want to try to take everything that you're told in that problem statement and break it up into these different variables. All right, so first thing to remember is anything with a subscript of 0, we assume is happening at time t equals 0. So in these equations, you'll see that we have x naught and y naught. So x naught is the x component of the position at time t equals 0. Similarly, y naught is going to be the y component of the position at time t equals 0. All right, anything that doesn't have a subscript of 0, so for example, you'll see x and y in these equations, those are things that are occurring at time t. Okay, so that's some later time, and t you'll see is also in these equations. So those two things are going to be linked to each other. X and y are linked to the time t. Those are the position at time t, really the x and y components of the position at time t. All right, then you'll also see in these equations we have v naught x and v naught y. So those are the x and y components of what we call the initial velocity. In other words, the velocity at time t equals 0. We also have Vx and Vy. So those are just the x and y components of the instantaneous velocity at time t. Last thing we have here are Ax and Ay. Those are just the x and y components of the acceleration, which is constant in time. All right, so a few more notes on using these equations before we kind of dive in a little bit. So firstly, we just want to really emphasize the fact that x and y motions are independent. And so what that means is that you never want to mix your x's and y's in the above equations. So that's, like I said, I mentioned already, we really want to think about what's happening in the x direction, what's happening in the y direction. Make two separate columns, right? Because you really just don't want to mix those two things together. All right, there is a way though that we can relate the motion in the x direction to what's happening in the y direction, and that's because they share a common time, right? So t in these two equations, that t is going to be the same in the two equations, right? So the way that we can relate the motion in the x direction to the motion in the y direction is through this shared time. And that's something that we're going to be doing quite a bit, which is why I have a star next to it. We'll be working on that a lot. All right, last thing to note here before we move on is that if you're told in a problem statement that you have constant velocity, remember acceleration is change in velocity per change in time. So if you have constant velocity, that means that you're going to have no change in velocity. In other words, your acceleration is 0. And so then you can go ahead and plug in that both Ax and Ay will be 0. Okay, and so then in the rest of our time today, what we're really going to be working on is applications of these 6 equations that are given in the teal boxes here. And I just would like to give a little disclaimer. Whenever you're problem solving, I would recommend coming back to these 6 equations in these 2 teal boxes. You won't want to use the equations that you're going to see a little bit later on in this lecture because those equations are going to be derived for very specific circumstances, whereas these 6 equations in the boxes here are very general, so they can always be used whenever you have constant acceleration in 2 dimensions. And so you really want to come back to these basic building block equations whenever you're problem solving. And I'll just make one final plug for doing things that way, which is that on your equation sheet, which you'll be given for exams, you will be given these 6 equations in the blue boxes here. You will not be given any of the later equations that you will see today. So really what I'm going to show you later, those are just showing you how you can apply these equations. They aren't meant to be equations that you memorize. Okay, so you'll just want to really come back to this slide whenever you're doing problem solving with 2-dimensional motion and constant acceleration. All right, so now we're going to take a closer look at a classic example of 2-dimensional motion with constant acceleration, which is projectile motion. So projectile motion is like the two-dimensional equivalent of free fall, which remember we studied as the classic example of motion with constant acceleration in one dimension. So to start studying projectile motion, first of all, we have to talk about what is a projectile. So a projectile is just an object that's somehow given some horizontal component of motion. So in other words, it's going to be something that's thrown, kicked, hit, or somehow launched into the air and somehow given some horizontal motion. All right, and then once the object has been launched, it's allowed to just fall freely due to the effects of gravity. So it's really going to be very similar to our one-dimensional free fall, except that this object is going to also have some horizontal motion. All right, but the only thing that's acting on it is still gravity. And so what that means is that it's only going to be accelerating in the y direction. Just like objects in free fall, it's going to have an acceleration in the y direction of minus g. So remember that's g is going to be the accelerational constant, so 9.81 meters per second squared, and gravity pulls objects towards the earth. And so when I say minus g, I'm assuming that the upwards y direction is the positive direction. So in other words, the pointing up direction is going to be positive y. And so then objects that are pulled towards the earth are going to have an acceleration of minus g, where that minus sign refers to the fact that the acceleration is pointing down. All right, nothing is acting on the projectile in the air. And so what that means is that it's not going to accelerate in the x direction. And so the x component of the acceleration for a projectile is always going to be 0. So these two things in the blue box, you're always going to want to think about acceleration in the y direction is minus g, acceleration in the x direction is 0 whenever you have a projectile. All right, and so then these two accelerations, so acceleration in the y and x direction, these assume that we can ignore air resistance and Earth's rotation. So the only thing acting on our projectile is assumed to be gravity. All right, and so what does this mean for us? Well, we're going to want to circle back to those equations of motion for constant acceleration. It looks like 6 of them, right? Because we have 3 for the x direction and 3 for the y direction, but really they're repeated here. And so what are we going to do with these equations of motion? Well, we're just going to apply the fact that whenever you have a projectile, so whenever you read a problem statement and think to yourself, okay, this object is thrown up in the air, it's a projectile. You immediately want to write down that you have two known conditions here. So you know that AY is minus G, and you know that AX is going to be 0. And so then you can plug those two things into your equations of motion that I have over here on the right-hand side of the slide, and that's going to simplify things a little bit. So we don't want to memorize these equations that I'm deriving here. I'm just showing you how you can apply these known conditions to our equations of motion for constant acceleration. So for our equations in the x direction, for motion in the x direction, I plugged in AX equals 0. For our equations for motion in the y direction, I plugged in AY is minus G. There's a little bit of algebra there. You can go ahead and look through it if you'd like. But the results here are going to be summarized in this table that I have shown. And so you can see that the fact that the acceleration in the x direction is 0, it really simplifies things quite a bit as far as the motion in the x direction is concerned. So you can see here that the x component of the velocity at time t, so that's vx, is going to be equal to the x component of the initial velocity. In other words, the velocity in the x direction isn't changing as a function of time. All right, we also get a nice simplification in our position as a function of time equation. The motion in the y direction isn't quite as simplified, but we at least have one less unknown, right? So at least we plugged in AY is equal to minus G, and so that's just another known quantity, and we've eliminated one of our unknowns. Okay, so what other types of information will you be given in projectile motion types of problems? So usually you won't be told that AX is 0 and AY is minus G. You just have to recognize this is a projectile, and so I know the acceleration in the X and Y directions. But you will often be given the launch speed and the launch angle. So the launch speed, we use the symbol V0. That's going to be the magnitude of the initial velocity. And then the launch angle, we use the symbol theta naught, and that is going to be the direction of the initial velocity. It's usually given to you above the horizon, or in other words, above the positive x-axis. Okay, so if we were to think about this cannon here, it's being launched, the cannonball is being launched out of this cannon. We know it has some initial velocity, v naught, It's a vector, the magnitude of that vector, so the length of that arrow is going to be the launch speed v naught, and then the angle above the horizontal is your launch angle theta naught. Okay, and so then we know that when we want to use our equations of motion with constant acceleration, knowing v naught, so in other words, knowing the launch speed and the launch angle, well, to use those equations of motion, we really need the components, right? We need the x and y components of that initial velocity. So we're going to have to break that vector up into its x and y components. And that's pretty straightforward. We can do that by drawing our nice little right triangle here, where we have the legs formed by v naught x and v naught y, so the initial components of the velocity in the x and y directions. The angle over here is going to be that launch angle, theta naught, and then the hypotenuse of that right triangle is going to be the magnitude of the launch velocity, or in other words, our launch speed v naught. So in general, you're going to be given v naught and theta naught here. Okay, so then looking at that triangle, we know our trig relationships tell us that cosine of theta naught is the adjacent divided by the hypotenuse, so that's going to give us v naught x over v naught, which we can rearrange to solve for v naught x, which remember we're going to need to use our equations of motion for constant acceleration. Similarly then, sine of theta naught is going to be v naught y divided by v naught, which comes from the fact that it's opposite over hypotenuse, and so we can rearrange and solve for v naught y. And so whenever you're given a projectile motion problem, first thing I would always do, write down my knowns, which is that the acceleration in the x direction is 0, acceleration in the y direction is minus g, and then you want to look for the launch speed and launch angle and immediately find out what is the x component of my initial velocity, what is the y component of my initial velocity. Okay, let's do a practice problem here. So we have an archer who takes aim at a target and launches an arrow with a speed of 48 meters per second at an angle of 20 degrees above the horizon. And we want to know what is the x component of the arrow's initial velocity. Okay, so to answer this question, I would always start with a little sketch. I love to do little sketches here. And so I would draw in an arrow and say that that arrow has a length of 48 meters per second. That's my launch speed, which is what we're told here. And then we know that the arrow is going to be launched at an angle of 20 degrees above the horizon. And so we can draw in our angle theta naught here. Then we can split this vector up into its x and y components, v naught x and v naught y. Looking at our right triangle here, we can solve for v naught x. We see that v naught x is going to be v naught multiplied by cosine of theta naught. V naught x is what we're looking for, right? Because we want to know the x component of the initial velocity. All right, and so then we can just go ahead and plug in our known values here. So we plug in 48 meters per second for v naught, 20 degrees for our launch angle, and you should get 45 meters per second here. And if you did that and you didn't get 45 meters per second, make sure your calculator is in degrees instead of radians. All right, so I would go ahead and pick answer B here. Okay, so let's look at another example of a projectile motion type of problem statement that you might be given, and let's practice pulling out known information from this problem statement. So here, as an example, we're told that our projectile is launched from the origin with a speed v naught at an angle theta naught above the horizon. Okay, so that doesn't sound like it's a lot of information, but it really is. So first of all, we're told about the initial position. So here it says it's launched from the origin. And so that's telling us about the initial position of this projectile. Specifically, it tells us that the projectile is initially at the location 0, 0, which is our origin. So in other words, we could immediately write down two knowns here. X naught is equal to 0, and so is y naught. So we have two knowns already. All right, next thing, initial velocity here. So as promised, we're given the launch speed v naught and the launch angle theta naught, which we know we can use to write down our initial speed in the x direction and our initial speed in the y direction. So if I were given this problem, that would be the next thing that I would do. We can do that, remember, by forming a little right triangle here. And so then we would know that v naught x, so that's the initial velocity in the x direction, is going to be v naught cosine of our launch angle. And v naught y is equal to v naught times sine of our launch angle. All right, so we now know x naught, y naught, v naught x, and v naught y. Remember, for any projectile, we can also write down the acceleration. So these are going to be our last two unknowns that we can pull out of that problem statement. So here we know that ax is going to be 0 and ay is going to be minus g. So we can really draw a lot of information out of that problem statement. And then what you would want to do is you would want to use those initial conditions or those known conditions here and plug them into your equations of motion for constant acceleration. Just as an example, I'm going to show you how I would do that here. So it's a little bit of algebra, and then we get this final result, which is shown in the table here. And so I would not recommend memorizing these. I'm just showing you how you could plug in these known values into those equations of motion. But you should know how to take a problem statement, read it, and pull out the relevant known information. So that's really what I'm trying to get at here. All right, so let's do another practice problem here. So again, we have this archer who's aiming at a target and launches an arrow at a speed of 48 meters per second at an angle of 20 degrees above the horizon. And we want to know the arrow's vertical speed after it has been in the air for 1 second. And so the first thing we want to do here is think about if you were asked just for what is the arrow's vertical speed after it's been in the air for 1 second, what variable does that correspond to in terms of those equations of motion with constant acceleration? Okay, so let's go through each of these options one by one here. So first of all, if we were to think about V naught, V naught, remember, is the launch speed. In other words, it's the magnitude of the initial velocity. Whenever we're talking about initial, that's at time t equals 0. So here we're specifically asked for time 1 second, right? So we want to know the vertical speed after it's been in the air for 1 second. And so we're not looking for something at time t equals 0. So this is not V naught. Okay, what about V naught y? Well, V naught y is just the y component of that initial velocity. Again, that corresponds to the time t equals 0. So this isn't what we're looking for either. What about just v? So v would actually be the magnitude of the total velocity of this arrow at time t, which is in this case going to be 1 second. So now we're getting closer. That's at least at the right time. But here we only want the y component. So we don't want to know the overall magnitude of the velocity, which would be the sum of the square of the velocity in the x direction plus the velocity in the y direction, and then you would take the square root, right? So that's the magnitude of the overall velocity of that arrow at time t. So that's not what we're looking for either. And so it must be Vy, and you might remember that just from our description of the different variables in our equations of motion with constant acceleration. Vy is going to be the y component of the velocity at time t. Here, our time t is going to be at 1 second. So this is, in fact, what we're looking for. That is going to be the vertical speed only of that arrow at time t equals 1 second. So I would pick answer D here. All right, now let's actually find that vertical speed after the arrow has been in the air for 1 second. Okay, so now we want to start solving this problem by listing out all of our known quantities from the problem statement. So first thing I would always write down in a projectile motion type of problem is that ax is equal to 0, ay is equal to minus g. Okay, next thing I see here is that we actually know the final time at which we want to know the vertical speed of this projectile. So that final time t is going to be 1 second. And so I would go ahead and write down that t is equal to 1 second here, which tells us how long the projectile is in the air at the point in time that we're interested in. Okay. Next up, I see that we are given the launch speed as well as the launch angle, right? And so I could immediately write down V naught, the launch speed is 48 meters per second. Theta naught, which is the launch angle, is 20 degrees. Then we know that when we have launch speed and launch angle, we need to find the x and y components of that initial speed. And so we can draw out our little right triangle here, and we can find that V naught x, remember, is going to be V naught times cosine of the launch angle, which gives me 45.1 meters per second. That was from our previous example. And then we can also find V naught y by taking V naught and multiplying by sine of the launch angle. Here that ends up giving me 16.4 meters per second. All right, so those are two more known quantities. And that's really it as far as things that we know from that problem statement. The next thing I would always write down is what is my unknown? In other words, what am I looking for? Because sometimes these problems get a little bit long, so it's really important to make sure you make note of what am I actually solving for here. And we already figured this out in the last problem. We said we're really looking for Vy. In other words, what's the vertical speed at time t equals 1 second? Okay, so next thing I would do is I would look at my list of knowns, I would look at my unknown, and then I would take that list of the equations of motion with constant acceleration, and I would look for an equation where the only thing that I don't know in that equation is the unknown that I'm actually looking for. And so when I do that, when I look through that list of equations, I would pick out the equation Vy is equal to V naught y plus Ayt, because I know V naught y, I know Ay, I know t, and I'm looking for Vy. So this is going to work out perfect for us. All right, the last thing we really have to do is plug in our known information here. So I've plugged in all of my knowns that I've listed out from up above, and I can solve directly for Vy, which I find is 6.6 meters per second here. And I'll take note here of the fact that this is a positive value, which means at this point in time, so after 1 second, the arrow is still moving generally in the upwards direction, even though it's accelerating downwards, right? So gravity's pulling it downward, and the effect of that is that you can see that this speed at time t equals 1 second is in fact less than the vertical speed was initially. So it is slowing down in the upwards direction. All right, so I would go ahead and pick answer C here, 6.6 meters per second, and it is moving up. Okay, last question here, last practice problem. So it's the same problem statement, and now we want to know how far has the arrow traveled in the x direction after it has been in the air for 1 second. This one's a little bit trickier. When we think about how far the arrow has traveled in the x direction, what that's really asking for is the displacement in the x direction, or in other words, delta x. So keep that in mind in solving this problem and just give it your best shot. Okay, so to start this, I would write down the list of knowns. It's exactly the same as in the last one, so you don't have to rewrite it. You can just keep the list from the last problem statement. So we have the same knowns as before. Then I want to write down my unknown, which as I mentioned is really going to be the displacement in the x direction here, or in other words, delta x. So delta x, remember, that's final position in the x direction minus initial position in the x direction. So in terms of our notation, that's going to be x minus x naught. So now there's really two ways that you could go about solving this problem. So there's two different approaches that you could use. The first option here is because we don't know anything about the position in the x direction, you're not told anything about that position. You could say, okay, let's go ahead and say that my initial position in the x direction is 0. So x naught is equal to 0. Then you could see that solving for delta x is going to be the same thing as just solving for the final position, x at time t equals 1 second in this case. So you could go ahead and do that. And so then I would look at my list of equations for constant acceleration, and I would pick out the equation x is equal to x naught plus v naught xt plus 1/2 ax t squared, because in that case I would know everything in that equation except for x, which would be the thing that I would be solving for. So that's a perfectly good way to go about solving this problem. Approach number 2 is to recognize the fact that in this equation that we have up here that I was just talking about, if you were to subtract x naught from both sides of that equation, you would end up getting x minus x naught is equal to v naught xt plus 1/2 axt squared. And then you recognize, oh, x minus x naught, that's delta x. So that's going to be the displacement in the x direction. And that's a little trick that's going to be useful to you often in these types of problem statements. So either of these two approaches will work. You can try it both ways. You'll get the same answer. I tend to prefer approach number 2 here. And so that's what I'm going to do. So approach number 2, I write down my equation that I have right here. I've rewritten it, and then we just want to plug in our known information. So first thing I can do is recognize ax is equal to 0. That's going to simplify things quite a bit because this whole second term in that equation is just going to be 0. Then I'm left with delta x is equal to v naught x times t. I know v naught x, I know t, I can plug them in, and I get delta x is equal to 45.1 meters. So I would go ahead and pick answer B here. Okay, now let's go ahead and look at another classic example here. So here's our problem statement. A projectile is launched horizontally from height h with speed v naught. All right, so what can we pull out of that problem statement? Let's do some more practice with that. So first thing I would want to think about would be initial position here. So whenever you're told that the projectile is launched from some height h, then what you usually want to do is go ahead and think about defining the ground level as the level where y is equal to 0. because in that case, your initial position, so remember that's going to be y naught in the y direction, you can say that your initial height, so that's y naught, you can say that that's going to be h. So that's what I would do in this type of problem. I would define the ground to be where y is equal to 0, and then say that y naught, the initial position in the y direction, is equal to h. Okay, then because we're not told anything about the position in the x direction, I would also go ahead and define x naught is equal to 0, so that the initial position of my projectile in the x direction is at x equals 0. So that was like approach number 1 from the last problem that we were just talking about. Okay, so those would be the first two things that I would write down in terms of my known quantities from this problem statement. X naught equals 0, y naught equals h, where I've defined the origin as drawn in this little diagram here. Okay, next thing I would do is think about initial velocity. Once again, you're given the launch angle and the launch speed, even though it may not seem like you're given that launch angle. So the key here is to recognize horizontally. That means that the launch angle is 0. So everything is just, it's fired in the horizontal direction. It's not given any vertical speed to start with, it's all horizontal. And so our launch angle is going to be 0 degrees. And intuitively what that tells us is that the entire launch speed is in the x direction. So in other words, v naught x, the initial velocity in the x direction, is exactly equal to that launch speed v naught. Also, we know that it's launched entirely horizontally, so the initial speed in the y direction, it must be 0. And you can see that this does fall out of the math, plugging in that theta naught is equal to 0 degrees. Okay, so then the last thing we can do is write down our acceleration. Because it's a projectile, we know ax is 0 and ay is minus g. All right, then we can take our equations of motion. Once again, I'm just going to show you how we could plug in these known quantities into our equations of motion and take a look at how things simplify. So I've got a little bit of algebra plugged in here. You are welcome to look through that at your leisure. Here's our result. So once again, we see that the velocity in the x direction is constant. We have even more simplification for our position in the x direction as a function of time, which is lovely. And you can see that we really get nice simplification for our motion in the y direction, since that initial velocity in the y direction was 0. So this is a really nice example. We like these types of problems. All right, once again, I'll say don't memorize these equations, just showing you how to plug stuff in. All right, let's do a practice with this type of problem here. So as an example, say we have a projectile that's launched horizontally with speed v naught from a height h above the ground, and we want to know how long is the projectile in the air before it lands. This is a classic. Okay, so whenever you see how long is the projectile in the air before it lands, really this can also be referred to as the time of flight of the projectile. So if you see time of flight, think how long is it in the air. All right, so how would we go about solving this? Of course, we're going to make a list of knowns. So first of all, we know our acceleration, of course, for our projectile. Then we're also told about the launch speed and the launch angle. Here it's launched horizontally, so our launch angle is 0, and the launch speed we're told is just v naught. So we'll leave that variable there. Okay, so then immediately we know we have to take that launch speed and launch angle and break our initial velocity up into its x and y components. So we can go ahead and do that. It's pretty straightforward. Since that launch angle is 0, we know that the initial velocity in the x direction is just v naught, and the initial velocity in the y direction is 0. All right, last thing we actually know from this problem statement is the initial position. And so here, when we think about the initial position, we can go ahead and define our coordinate system. Like I mentioned, whenever you're told the launch height, it's usually convenient to define the ground to be where y is equal to 0, so that when you think about the initial position, the initial y position is just going to be the height h from which your projectile is launched. Similarly, it's convenient to define the origin so that x naught is at 0. Okay, so I would go ahead and write down that we have defined the initial position in the x direction to be 0, the initial position in the y direction to be h. Last thing we actually do know here, so there's a lot of information packed in that little sentence. So the last thing we know here is that our final time in this case is going to be where the projectile lands, or when the projectile lands. And so when it lands, we already said that the height of the ground is at 0. So in other words, when the projectile lands, that means we want y to be equal to 0. So in other words, the final position in the y direction when the projectile lands is going to be at y equals 0, which is where we defined our ground. Okay, Now we're ready to think about our unknown, which is t, which remember that's the time it takes for the projectile land, or in other words, the time it takes for the projectile to get to y equals 0. How am I going to go about solving this problem? Again, I would pull up my list of equations, so those 6 equations, really it's 3, but you got a set for the x direction and a set for the y direction, and I would look for an equation where the only thing that I don't know in the whole equation is t. So when I look at that list, I would pick out the equation y is equal to y naught plus v naught yt plus 1/2 ay t squared, because the only thing I don't know in that equation is t. Then I would go ahead and plug in my known information. So I've plugged in all my knowns here. Simplifies a little bit, this middle term is going to go to 0, so we get some nice simplifications. We can go ahead and rearrange and solve for t. Originally I solved for t squared, I ended up getting 2h over g, and then you take the square root of both sides to get t by itself. So we end up with t, the time of flight, is equal to the square root of 2h divided by g. This is going to be the time of flight for a projectile that's launched horizontally from a height h above the ground. Okay, and so a lot of known initial conditions went into deriving this equation. So once again, I wouldn't recommend just kind of using this equation. I would definitely recommend going back to our basic equations of motion if you're ever asked for the time of flight for a particular projectile. All right. Another thing you might be asked for is something called the range. So let's take a look at a sample problem statement that's asking for the range of the projectile. So again, we have our projectile launched horizontally with speed v naught from height h, and now we want to know how far does the projectile travel before it lands. Alternatively, you might just be asked for the range of the projectile. So when I say range, it just means how long does it travel before it lands. Okay, and so if we were to go about solving this problem, we could write down the same knowns that we had for the previous problem. It's the same initial problem statement. So we could write down our same known conditions. So if once again we've defined the initial position of the projectile to be at x equals 0 and y equals h, then when the projectile lands, that's going to be at y equals 0, right? And we know that the time that the projectile lands is given by the time of flight, which we just calculated by studying the motion of this projectile in the y direction. All right, and so now we're going to use that time of flight to determine the range of this projectile. And this is something that you're commonly going to have to do. If you were to just be asked for the range without being asked for the time of flight first, if you looked through your list of equations, you would notice that there wouldn't be any equations that you could use to solve for the range because you wouldn't have enough knowns. So you would always have an unknown of the final position of the projectile and also the time. So you wouldn't have enough information. And so that would tell you that you need to find the time by thinking about the y motion of this projectile. All right, so we've just broken it down into steps here. Okay, so next up, we want to write down our unknown, which is x. So remember, that's the final position of the projectile, or in other words, the position of the projectile at time t equals the square root of 2h divided by g, which we already found out is the time when the y position of the projectile is at 0. Okay, once again, you want to look through your list of equations and look for something where the only unknown is x. So in other words, the position at time t. Here we would end up with this equation, x equals x naught plus v naught xt plus 1/2 ax t squared. Then we could start plugging in our knowns. So immediately I would plug in my ax equals 0, which is going to get rid of that whole last term, which simplifies things quite nicely. Also, because we defined our projectile as being launched from the origin, x naught is going to be 0, which also simplifies things quite well. All right. Then all you have left to do is to plug in t is equal to our time of flight, which we got by studying our motion in the y direction, and we find that the range for this projectile launched horizontally from height h is going to be v naught multiplied by the square root of 2h divided by g. So in other words, that's going to be this distance here along the x-axis from the place where your projectile is launched. Okay, so those are some classic examples of projectile motion types of problems that you might be asked to solve. We're going to be doing tons of examples in class over the next couple of days, so don't worry if it feels a little overwhelming. I promise it does get easier once you've done a couple. But to wrap up for today, I just want to talk about the shape of the trajectory of a projectile. So you may have noticed I've had different pictures and diagrams of projectiles, and they all follow this parabolic shape. And so now we just want to answer the question, why is that the case? So where does that come from? And so to do that, we're going to have to relate the position in the x direction to the position in the y direction. And remember that the way that we can relate our motion in the x and y directions is through their shared time. So that's what we're going to do. This derivation, there's a little bit of algebra here, so don't worry too much about it. It's just going to show you why we get these parabolic trajectories. Okay, so let's start with our basic equation of motion in the x direction. I've already plugged in the fact that ax is equal to 0 here to find that x is equal to x naught plus v naught x times t for our projectile. Next, I'm going to make the simplification that we're launching this projectile from the origin, so x naught is going to be equal to 0. All right, and then I want to find the time in terms of position so that I can relate position in the x direction to position in the y direction at a particular time. So all I've done is I've taken this middle equation and I've rearranged to solve for t, which we see is equal to x divided by v naught x. All right, now what I want to do is I want to eliminate time in my y equation for position as a function of time. And to do that, I'm just going to replace t with x divided by v naught x. And so this way we can relate our y position to our x position at one particular time. Okay, and so then I could go ahead and do that. Like I mentioned, there's a little bit of algebra here and it looks a little bit ugly, but the basic effect that we end up getting is that y, so that's our position at a particular moment in time, is equal to a constant plus a constant multiplied by x plus another constant multiplied by x squared. And so that looks exactly like the equation that you would get for a parabola. Y is equal to a plus bx plus cx squared. And so that's why whenever we show these projectiles, we show their trajectories through the air, they always look parabolic in shape. It's because if you were to relate x and y at a moment in time and then let that time vary, so if you were to plot y versus x as a function of time, you would always end up getting this parabolic trajectory. So I've plugged in some numbers over here. So I've plugged in some sample numbers for our initial conditions of y naught, v naught y, and v naught x, and I've produced the resulting graph of a parabola down below. So that's why we always end up getting this parabolic path for our projectile motion. Let's wrap up with one last problem for today. We want to know which of the following graphs of position as a function of time would describe the path of a projectile. Okay, so if we were to look at these three graphs here, I would recognize that graphs A and B are parabolic, whereas graph C looks pretty linear. So I would say graph C is probably out as far as our projectiles go because we know that they follow parabolic paths. So I would go ahead and pick answer D. It could be A or B here. All right, that's it for today. Like I said, we've got lots of practice problems coming, so look forward to that, and I will see you guys in class.